In this goal, we are going to be looking at the ideal gas law and then adding the concept of molar mass or molecular mass to the ideal gas law and also density. Recall for the molar mass, you look on the periodic table and you take the formula and you add up each of the individual elements, and that will be the molar mass or the molecular mass of your molecule or your compound. The units for the molar mass are grams per mole, and in PivNert, N is moles. So we can take and rearrange it to solve for moles, and we get this. And we can insert that right into PivNert. And when we do that, we get this equation right here. So we have M for mass. Sometimes you see it as a G for mass because you are using grams. And then, of course, the ideal gas law constant, R, and then temperature. Remember to always use Kelvin for temperature. And then we have our molar mass on the bottom. We can rearrange this equation to get this. So MVP equals MRT. Another symbol for molar mass is a cursive capital M. So this stylized M there represents the molar mass. So you can remember this formula by MVP Mr. T. So again, the molar mass times the volume times the pressure equals the mass times the ideal gas law constant times the temperature. Now for density, we can put density into the formula. And when we look at density, density is mass divided by volume. So we can take and solve for volume because volume is what we see in PivNert. And when we do that, we get this right here substituted for density. That's equals D. And so we can get this equation where molar mass equals density times the ideal gas law constant times the temperature divided by the pressure. And you can remember this equation by dirty P. So MVP, Mr. T, and dirty P, these two formulas should help you with your molar mass and also if there's density. In a previous unit, we used the percent composition data to help us find the moles, and then we found the empirical formula mass after you found the ratio, and then we were able to write the molecular formula. So we can incorporate this also into PivNert. All right, let's revisit density just a little bit. So the density of a gas, it's directly proportional to the molar mass. So as a child, I was always very frustrated that when I blew up a balloon, it didn't float. I mean, some balloons floated and some didn't. How come I couldn't make a balloon float? And so this is because when you exhale, you're exhaling mostly nitrogen, but also some carbon dioxide. And so you end up with your exhale breath a little bit more dense than the air around it. So that's why you can't just blow up a balloon and have it float. However, a helium balloon, its molar mass is very, very low. Because of this, it has a density less than air, so it will float. It will float on the air. And so this means if you let a balloon go, it will just go up into the sky because it just keeps floating on the air. So density is inversely proportional to temperature also. So this is what gives hot air balloons lift. As they increase the temperature in the envelope of the hot air balloon, this decreases the density because the gas molecules spread out more. They're moving quicker and they hit the size of the container with more force and also with more collisions. And this causes the lift for the hot air balloon because the density will be less than the air surrounding it. Let's look at this problem that has density in it. Find the density of nitrogen gas, and remember, this is one of those diatomic elements, so the formula is N2. So the density of nitrogen gas at 20 degrees Celsius and 115 kilopascals. So kilopascals is not a pressure unit you would see on the AP test, but we do use it in the lab, so I do want you to become familiar with this. The conversion is 101.3 kilopascals is equal to 1 atmosphere. So let's go ahead and do that conversion. So when I'm doing a conversion factor, remember the two values that are stacked on top of each other should equal 1. So I have kilopascals on the top and kilopascals on the bottom, so they will cancel. That's why I arranged them that way. And I'm left with atmospheric units. And the answer to this is 1.135 atmospheric units. I carried some extra significant digits just so that I don't have rounding errors. Next, let's look at our temperature. So our temperature, we cannot have it in degrees Celsius for any sort of gas law problem. You must always be in Kelvin. So I'm going to take 273 and add 20 to it, and this will be my temperature in Kelvin. So 293 Kelvin. All right, so we're going to start off with our dirty P equation. And we're going to rearrange this to solve for density. So up here. So I'm going to get density equals our pressure, which we just found. And I'm going to multiply this by the molar mass. So N2 molar mass would be 14 times 2, so 28 grams per mole. Make sure that you include all the units in all your ideal gas law problems. And then we are going to divide that by the ideal gas law constant and then multiply it by the temperature that we found. Our units should all cancel. Whoops, liters doesn't cancel. Atmospheres. And is that all I can do? Moles. There we go. So notice what's left. What's left is grams divided by liters. So that is a density unit. Remember, density is mass over volume. And so I should have two units, a mass unit divided by a volume unit. And the number for this problem, we end up with 1.32 grams per liter. That is 2 sig figs. My temperature is only 1 sig fig. I'm going to just put a little decimal there so I have at least 2. So it would be better if I express this as 1.3 grams per liter. There's my answer. Okay, let's try this problem. So this is incorporating percent composition with finding the molecular formula, and you will have to find the molar mass using PivNert. So the first thing we need to do is we need to take these percentages and we need to change them to grams, and then we need to find out how many moles they are. So we have 42.1 grams, and I divide it by the molar mass of carbon, and I get 3.5 moles of carbon. Let's do the next one. Again, take that percent and just scribble it out and put G for grams. So I divide by the molar mass of hydrogen, and then I basically just change that into moles because hydrogen just has 1 gram per mole. And let's do the nitrogen. Scribble out the percent, put G for grams, and we have 14 grams of nitrogen. And last but not least, we have oxygen that's going to be there. And they don't give us how many grams. This is kind of a not nice problem. So we need to take 100% and subtract 42.1, 5.26, and 24.6. And that will tell us the percent of oxygen. And when I do that, I get 28.04 grams of oxygen. Divide by the molar mass of oxygen, and we get 1.75 moles of oxygen. Last but not least, we need to figure out the molar ratio. So I need to divide by the smallest number, and it is 1.75. And dividing all of these bottom two are going to be 1. They're going to be close enough to 1. And then carbon is going to be 2. And hydrogen is going to be 3. So I can write my empirical formula as what this solves. So I have C2H3NO. All right. So let's go ahead and find the molecular mass, because we need to find the molecular mass in order to find the molecular formula. So let's go to our MVP, Mr. T formula, because this is the one that has the molecular mass in it. So that M means molecular mass. And we are going to rearrange that to solve for just the molecular mass. So I'm going to divide through by my pressure and volume. And then I can plug in the mass that they give us. So the mass is 0.232 grams. And I have my R, and darn it, I don't have enough room. I'm just going to stack them. And then my temperature. My temperature is 99 degrees Celsius, so I'm going to change that to Kelvin. All right, so these are all multiplied, and I'm going to divide that by the pressure and the volume. So the pressure is 745 millimeters of mercury. We need to change that to atmospheres. So I'm going to divide this by 760, and I get for my atmospheres 0.98. All right, so let's go over here. So we have 0.98 atmospheres. And then I'm going to divide it by the volume, which is 0.125 liters. Okay. When I go ahead and do the math, I get 57.8 grams per mole. So all the units should cancel out. So let's see, liters cancels out, atmospheres cancels out, Kelvin cancels out, and I'm left with just grams and moles. So you see, if you write the units, then you know that you have the right answer. So I know molar mass should be in grams per mole, and that is what my ideal gas law helps me get. All right, so that is our molar mass. So to find out the molecular formula, you need to take the molar mass and divide it by the empirical formula mass. So I need to add up 2 carbons, 2 hydrogens, 1 nitrogen, and 1 oxygen. So over here, when I add those up, I get 57.8. So I essentially have 57.8 divided by 57.8 equals 1. So that tells me that the molecular mass and the molar mass, or the molecular formula and the empirical formula, they are both the same. So my answer is C2H3NO. Volumes of gases involved in reactions, you can use their balanced equations to help you solve the problems. So just because we've moved over to ideal gas law problems, it doesn't mean that we can't also have a balanced equation where we use the molar ratio. So let's look at this. So it says what mass in grams of ammonia can be produced from 22.4 liters of nitrogen at 25 degrees Celsius and 1 atmosphere. This is standard pressure, but this is not standard temperature. So we need to use Pivnert for this. So PV equals nRT. And I need mass in grams. And I know that if I solve for moles, then in my Pivnert equation, then I can later on turn it to grams. So let's rearrange this to solve for moles. So we have PV over RT. And let's plug in what we know. So we have 1 atmosphere, and we have 22.4 liters, and our R. And our temperature, we need to change that to Kelvin. So add 273. And I get 0.0409 moles of N2. So now it's just a matter of looking at our balanced equation. And I'm just going to clear up some room here so I have some room to write. We're going to look at our balanced equation. And I'm going to change that to grams. So this is nitrogen that we've been working with. So let's go ahead and use our balanced equation. And I have, for every 1 mole of nitrogen, I have 2 moles of ammonia. So we're wondering about the ammonia, so we got to change it to the ammonia. And moles cancels, but so does the nitrogen. So now we have ammonia, and it's just a matter of finding the molar mass of ammonia. Molar mass of ammonia is 17 grams for every 1 mole. And so when I go this moles to grams, I get 139 grams of an NH3. So that's my answer. So again, I first used PivNert here. I found moles, and then I used my molar ratios in my balanced equation to help me convert from moles of nitrogen to moles of ammonia, and then I converted from moles of ammonia to grams of ammonia. All right, another problem where we're using the balanced equation. So it says how many liters of oxygen measured at, there's my pressure, and then here's my temperature. Remember, we need to be in Kelvin, so this is going to be 297 Kelvin. And required to burn 1 gram of octane to CO2. So the equation is not given to us because I accidentally erased it. So let me go ahead and give it to you. So they would not have you write this. They would give this to you. So don't panic because you're like, this is a combustion reaction. So we get CO2 and water. And there's our octane. So that's like gasoline. And you can see the combustion reaction, oxygen, CO2, water, and of course I have my hydrocarbon. Okay, so our starting value is 1 gram of my octane. And I want to somehow get to oxygen. So let's get to oxygen. So when I add up 8 carbons and 18 hydrogens, we're going to get 114 grams. And that is equal to 1 mole. And now when I look at the balanced equation, I am going to cancel out my moles of octane and change it to moles of oxygen. So, because again, that's what my question is. How many liters of oxygen? So in the balanced equation, for every 2 moles of the octane, I have 25 moles, that's a little crazy, of the oxygen. And I end up with 0.110 moles of oxygen. Okay, now they gave me all this pressures and temperature data, so I know I can use PivNert. And it wants how many liters, so in other words, what's the volume? So solving for liters, I'm going to, or the volume, I'm going to divide by the pressure, both sides. And now we can just plug in our values. So we just found the moles of our oxygen, and then our ideal gas law constant. And our temperature we already found was 297, and divided by our pressure, which is 740 millimeters of mercury. Because I'm in atmospheres right there, let me write that in a different color so you can see it. Because I'm in atmospheres right there, I need to change, I should have changed this millimeters of mercury. I can do it right here. I'm just going to divide it by 760 millimeters of mercury. That will give me atmospheres. Okay. So when I go ahead and work this out, so my moles is going to cancel, my temperature cancels, my liters is what I'm going to be left with. And when I divide my millimeters of mercury here, I will end up with atmospheres, which will then cancel. Okay, sorry, I should have converted that before I stuck it in there. But my answer is 2.75 liters. So again, using the balanced equation, those molar ratios to go from, in this case, one reactant to another reactant. This is the theoretical value of moles I would use for my 1 gram of octane. And I could figure out what volume it would take up, which is 2.75 liters at this particular temperature.